Okay, so before starting, I'd like to congratulate Sajid on her baby girl. We're very excited about her and can't wait to see more of her. Um, okay, so today I'm going to talk about my experience in semiconductor manufacturing, and I've worked in only one company, so I'll just talk about my experience there. So here's a little blurb about myself, my education and career so far. As Sajid already introduced me, I had my B.Sc from BUET in electrical engineering in 2009. Uh, I worked with Dr. Kamrul Huda and Farsim Manan Mohammadi for my undergrad thesis. And I'm specifically mentioning these two people because they were kind of directly responsible for setting me up in the path of process engineering, because as you can see, my undergrad thesis was also in diffusion process modeling. So I kind of stayed in that path. Uh, I went to University of South Carolina and got my PhD in electrical engineering in 2014. I worked on silicon carbide material. It's a wide bandgap semiconductor used mostly in the power device industry uh, for its high voltage, low leakage applications. And my project was funded by a government organization that were looking for nuclear radiation sensors. So I actually looked at devices that implement that used like Schottky interfaces and different heterojunctions like graphene silicon carbide interfaces. So my focus of the PhD was silicon carbide epitaxial growth, and also I worked on some interface defect characterization. After PhD, I joined Intel Corporation in 2015. I'm still working there now. I started as a plasma etch process engineer, and I'm currently working as a process integrator. I will talk more about these job roles later on. So before going to a brief company overview, I'd like to show you the silicon landscape, how the industry is kind of. So I'm going to talk about mostly semiconductor manufacturing. So I can divide that process if you look at the, let me bring up the pointer. Yeah. So in this middle column, I have all the major semiconductor manufacturing companies that sells semiconductor chips, and I divided up the function of these companies into four blocks. One is chip design, manufacturing, then assembly and testing, and then marketing. By marketing, I mean direct to consumer. When you go to the market and buy products, looking at their brands. So in the first group, we have the IDMs, integrated device manufacturers. At the beginning of semiconductor industry, actually, all of the companies were IDMs. They used to design chips on their own, manufacture them, assemble and test them, and then sell to the customer. Then eventually, some of the companies grew specialization in manufacturing, and we are calling them foundries. Example of foundries are TSMC and Global Foundries. And because we have foundry service, we have in the recent times the fabless companies that sell chips, but they do not manufacture them on their own. They just design it and then send it to the foundry to manufacture for them. And the most of the semiconductor companies that you see today uh, belong in this category, like AMD, NVIDIA, to all the way to Apple. Apple is also a design house. They design their own chip. Then on the consumer side, we have these more familiar brands like Apple, Samsung, Dell. We call them OEMs, original equipment manufacturers. So they're experts in system design and system building. So they make laptops, finished products, uh, and they kind of buy the chips from these companies. But some of them have design capabilities, and all of them, sell directly to the consumer. So when you buy a product, you see their brand on the consumer products. Now, on the back end of everything, there are vendors and suppliers, and we do not see them at all when we go to the market to buy products, but these are very important part of the semiconductor ecosystem. So they supply materials, equipment, design tools like CAD tools. For example, I think in when we were in Wood, we used to use CAD Cadence. Uh, this is also used in semiconductor industry very widely for simulation and stuff. So all these companies that provide these services, fab equipment, they belong to the vendor and supplier category, and they supply the manufacturing industry basically. Now, what does my company Intel do? Uh, Intel is an integrated device manufacturer. That means Intel has its own design wing. They design their own chips, go through the manufacturing process, does in-house assembly and testing, and then sales to consumers. And by our customers not only include common people, also the OEMs like Apple and other companies. They also buy our chips to make their devices. Now, a little bit of history of Intel. I think these are very well known. Intel was founded in 1968 by Gordon Moore and Robert Noyce. Here's a picture of them. The name Intel uh, is a contraction of integrated electronics. When they were first deciding what the name would be, the first suggestion was Moore Noise, but that sounded like more noise, so they didn't like it, so they went for this. Uh, the first Intel microprocessor was Intel 4004. It came out in 1971. It was not actually designed in Intel. It was designed by a Japanese company. They bought the IP rights for that. But this one did not find very widespread use because personal computer was not a thing back then. And it was used mostly in calculator and one pinball machine in USA. Uh, then the uh, biggest one that kind of started the Intel's path toward processor manufacturing is 8086, and x86 architecture was born there. And IBM brought up the first product based on a variation of this, I think 80826 in 1981. Uh, After that, there has been decades of transistor innovation. Intel is known for that, and known for kind of keeping up with the challenge and the promise of Moore's law. Uh, so Intel is mostly known as a processor company, but currently our product portfolio goes way beyond processors. We produce processors for servers, and we also provide networking devices, different kinds of adapters and transceivers. And we also have a very strong portfolio of memory graphics. We actually own the second largest FPGA company in the world, Altera. And we have FPGA products. Those are used as accelerators and data centers and stuff. And the most exciting, over the next decade, this will be very important. We are building systems for IoT, automated driving, and AI systems. So here are some of the examples of our products. I think this is a little bit outdated, but gives you an idea. So what we realized that as the hunger for data increases in the world, because of the widespread connectivity and connected things, automated driving, artificial intelligence, cloud computation, we see ourselves turning from a PC-centric company to data-centric company. So that is our focus going into the new decade in the 2020s. Okay, why I chose Intel to start my career? Yeah, the obvious reason was out of grad school. That was the first job offer I got. And yeah, that was the easy decision. So the reasons I'm showing here, they're more like why I stayed here. So the first one is obviously working at the cutting edge. I work with some of the best minds in the industry, and I'm very proud of that. The other big thing is alumni support and community. We have a good number of Guatians working in Intel, and anytime you want to network or you just want any sort of support, you have this huge community, very capable and very ready to help you. So this is a great resource you have to keep in mind when you're, going into your career. The other good thing is work-life balance. It actually consists of many different things. You have to have job security, good pay, to not worry about other things. You have to have, good, uh, time offs and other uh, provisions to make your life fruitful as you work here, and you're not not enjoying your life, so you're working so hard. So Intel provides good opportunities in that regard, so that's one reason to stay here. And another attraction for me to come here in Hillsboro, Oregon is a very beautiful state. It's very cloudy and foggy most of the year. It's still very mysterious, but the summer is heavenly. Uh, another, I just put that as an honorable mention. Of course, this did not influence my decision of joining Intel, but I really like this, Intel's corporate responsibility. Intel was one of the first companies in the industry to ensure gender pay equity, and they also made their supply chain conflict free. So the minerals that we're buying, we made sure that they do not use child labor or they're not from war zones in Africa. And also we have a great drive to carbon neutrality. So these are things that are close to my heart, and they really resonate with my values. Now, what do I do at Intel? Excuse me. So to explain that, let me talk a little bit about a typical technology cycle of semiconductor technology, for example, for 40 nanometer, 10 nanometer. Uh, so at the beginning, we have the pathfinding phase when the transistor innovation happens, like what new structure or new material we're going to use. We're looking at it. And before making any significant investment, we want to make sure that it really has the potential. So that is the pathfinding phase. After the innovation phase is done, it goes through a very long and tedious technology development process where we debug process defects. You have to find each defect mode and have a long-term fix for those defects. So eventually your process yield, which is the number of working die on a wafer, ramps up, and when it reaches a certain maturity, then you can produce wafers using this technology at profit. And at that phase, it enters the high volume manufacturing. So for my job role, I kind of straddle between the pathfinding and process technology development. So I work in process and flow development and de-risking the pathfinding projects, optimizing them, and making them scalable, and then taking that all the way through that TD barrier and making it manufacturable for high volume. Now, let's talk about transistor technology pathfinding. So this is mostly what we talk about when we talk about transistors, right? Transistor scaling and stuff. So the role of pathfinding is mostly to find new process flow, new material systems, device structures, or process capabilities like EUV. Uh, uh, so our industry is a little bit different from any other industry in terms of pathfinding, because we kind of have a guiding light, which is called Moore's Law. Uh, that is basically a development roadmap that the semiconductor industry has been following since the 1960s. So we have known from the beginning that if you shrink the size, feature size of the transistor, like the channel length and width, you can derive some circuit parameter improvement from that. Uh, uh, as you can see in this table below, this is the Denner scaling table, constant field scaling. So there are some pretty attractive scaling that you can get by shrinking the device size, like the gate delay or power density. Uh, these were all known, but there was what is the motivation for pursuing this very aggressively? And that actually came from the 1965 paper of Gordon Moore. He kind of clarified that as we increase the density of the chips, the manufacturing cost goes down. And he kind of charted the progress in the semiconductor industry in the 1960s in terms of scaling, and he saw a linear trend. So at that point, the scaling was basically a lithography scaling. So the lithography was very, primitive at the time. People used to draw layers in, markers in on overhead projector slides, and then use them as template. So as the lithography makes progress, we can expect the device size to go down. And he just made a projection into the next decade, 1975. And this was a fair projection because we already knew that if we scale the transistor, we improve the performance, we improve the density. So it is a very commercially viable path. But what is surprising is that the semiconductor industry kept doing it for another 2 decades, all the way through the 90s and through the new millennium. And and we have seen, process nodes shrinking. In 1965, I think it was 100 micron, and in early 2000, it reached 90 microns. So that's 1,000 times scaling in terms of device size. Now, the process node numbers that we use today, like 45, 32, 22. And if you notice, they actually scale by a factor of square root of 2. The reason is very simple. If you shrink, length and width of the channel by square root of 2, you get an area scaling of 2. So basically, you cut the area by half, and you double your transistor density. Now, these process node numbers used to correspond to the channel length, which was defined by the gate width or the gate half pitch through the 90s in planar transistors. And all these assumptions of scaling do not take into consideration the short channel effects. But in the 2000s, we reached a point where the short channel effects became significant. So we needed to make some material and structural innovations to keep scaling. So right now, if you look at the nodes, like if you take a 10 nanometer wafer, you cut it, you cannot find a feature of 10 nanometer. What you can find is a device that is capable of, if you think about a theoretical planar transistor of 10 nanometer that doesn't have any short channel effect, what would the performance of that transistor be? That is being delivered by a different structure, different combination of materials, uh, but at the same density. So that is the thing. It is an equivalent of an idealized planar transistor. You can look at it that way. So here's Intel's path to 10 nanometer from the early 2000s. I charted the major changes that the process underwent. So in the early 2000s, we still had the planar transistor, 90 nanometer and 65 nanometer technology. We introduced strained silicon. So the mobility of the channel went up. So even though the electric field was creeping up because of shrinking, because of the higher mobility, we could push more current through the channel. So that kept the scaling alive. But in 45 nanometer, even that was not enough. Our oxide was too thin, and our polysilicon gates were getting depleted because of the high electric field, because the device, the structures were very small. So we introduced high K dielectric and metal gate to replace the gate stack. Uh, in 22 nanometer, even a more disruptive change, FinFET. So we turned the channel sideways. So now we have gate control on 3 sides of the fin, and the effective area of current conduction increased significantly. So that drove scaling to 22 nanometer, and we have been using FinFET through 10 nanometer. And as you can see, the fin size and shape kind of evolved. Starting from 14 nanometer, we are calling this hyperscaling, which is not one change. There are multiple innovations that go into it. And if you're aware of the trends, the front end are the fin structures and gauge structures are not the major bottlenecks anymore. There are other problems related to like metal stacks. There are other challenges. So all of them put together, we are calling that hyperscaling. In 10 nanometer, we scaled the fins further. They're now taller and uh, thinner. And also, we have some major innovations like if you look at a layout, if you're familiar with the VLSI layout, we are used to putting the via outside the active device area. In 10 nanometer, that gate contact via came directly on top of an active device. So that gives us a pretty large amount of shrinkage. So, but one of the major criticisms of Moore's law is that it kind of stopped working in terms of many parameters like single core performance or the processor speed that kind of stagnated in the early 2000s. But from an industry perspective, if you look at uh, uh, the scaling of manufacturing cost, we are still on a downward path. So our motto is keep calm and carry on for now. I have added the citations of the relevant papers here. If you're interested, you can look them up. They all appeared in IEDM or VLSI. These are IEEE conferences, so you can look them up in IEEE Explore. Okay, now this was pathfinding, which is kind of the tip of the iceberg that everyone talks about, right? New transistor innovation and stuff. But in research labs, we have made transistors up to gate length 1 nanometer already. So what is the big deal about 10 nanometer transistor? The big deal is you cannot just make one transistor. For a processor to work, you need millions of working transistors. The current 10 nanometer technology packs 100 million transistors in a square millimeter. So, which is a huge challenge, and much of our company time and energy and resources are spent on making the process capable of high volume manufacturing. So the biggest tool that we use for that is called process control, which is actually the control of the variation in a process. So we divide the process into many smaller segments, and we look at the critical dimensions at each segment. For example, fin height, fin width, things that are measurable by non-destructive metrology tools. For example, we can do ellipsometry type of characterization and look at defect density, CDs, whether we are making appropriate connections between layers, those type of things. And the way we monitor them is we plot them in a control chart like this. So what a control chart is, we have a target value, which is we want the process to run kind of around that. So for example, if you're asking the process to create a 10 nanometer feature, it may not create 10 nanometers. Some of the wafers will be 9.98, some of them will be 10.02. So if you just chart them, they will look like random fluctuations. But there are there are thousands of layers in a transistor, and any irregularity in one layer kind of trickles down all the way and causes a lot of variation in the process. So we try to identify the root cause of that variation. And in that chart, we kind of put a couple limits around the 3 sigma mark of the process. And we do not let our process drift above or below that 3 sigma limit. So every time it goes above or below, we take some action. We kind of drive some sort of root cause identification and try to figure out how to resolve that. So there can be many different types of irregularities, like points running very far off, or some trend that is not uniformly distributed around our mean. So we try to fix them and push it back to the mean. So our process kind of runs symmetrically around the mean. So when you do variation reduction in multiple layers, the cumulative effect is that your process variation overall goes down, and you kind of converge to a mean value. So when the variation goes down, our sigma actually scales with that. So this is the very important feature of process control. The lines that we draw, that this is, we will not tolerate uh, excursion beyond these points. These are actually moving lines. As we mature the process, the sigma goes down and we tighten the chart. So it gets tighter, tighter and tighter and tighter, and at some point we get a very uniform and very low variation, low defect process. Another component is within wafer non-uniformity. Our currently we have like 300 millimeter wafers, which are pretty large. So your process tools has to be capable of creating the same feature everywhere on the wafer, center to edge. They have to look similar, but unfortunately they do not. So we need to identify what tool or what layer is driving that difference, and we try to patch up the gap. Or if there is any localized defect, we identify the root cause. So it is a process of continuous improvement that continues all the way through the HVM. So the innovation does not just go into transistor invention; it continues all the way through HVM. So that's pretty much everything I have for today. I want to leave this parting word from one of our founders, Robert Noyce. Don't be encumbered by history. Just go out and do something wonderful. I think that is also, true for our personal lives. Like whatever happened yesterday is yesterday. We just need to go out and do something wonderful today. Thank you.
Thank you so much, Omar, first of all, for your really nice presentation. And I think working a little bit on semiconductor manufacturing in laboratory scale, I can really appreciate the guys' work that you guys are doing, pushing the limit tighter and tighter to shrink the devices, and it's getting more and more challenging day by day. So it's a really nice talk. I invite everyone to ask questions in the chat box. At the end, we would have an interactive discussion. And